Okay, y'all ready? Get started? Just a few updates. Last week's video, I didn't post that on YouTube till this morning because there were some issues. Usually I can VPN network into my computer from home. I can get to my computer here, but for some reason I couldn't get in, and so I couldn't upload the video. But I did that this morning, and then also I just put into our class files the review for exam 2. So that's posted there. This is a layout of the next 4 weeks. So we have today, we're going to do quadratic functions and applications. And then we have a 4th of July holiday this Wednesday. So we only meet today, this week, and that's it. Pretty sure that's on the calendar too. Yeah, so we actually lose an entire week of class because of that holiday, because each day is equivalent to a week. And then we're supposed to have a week from today exam 2, which would cover factoring, solving quadratic equations, and then what we do today. I put a question mark there because I was going to talk to you all and see if y'all wanted to move exam 2 to next Wednesday and then do polynomials on Monday. Yes. You'd prefer to do that? Yes. Let's take a vote. Show of hands. How many of you would like to see these two switched? Polynomials would be on exam 2, but what we do with polynomials in here, I think you would be happy to see it. Like the material is kind of easy. I wouldn't say easy, but it's easier, I think, than the quadratic part, because we kind of baby it a little bit, if that makes sense. So it's just a matter of like recognizing things and counting numbers, and most students do okay with it. So it would help. I think it would help your grade to have polynomials on the exam. Personally, that's what my experience with that section is that you would like to see those on the test. So now, how many of you are like adamant about having it on Monday? Like you really would like to have the test on Monday? Anyone? Yes? Are you not going to be here Wednesday? Or are you going to? Okay. Okay. All right. All right. Well, let's plan for that. Let's see how today goes, but let's plan for switching these two. All right. And depending on how much time we have today, I might even be able to start the polynomials so that you can kind of see what it's going to be. And then the following week is where we're going to do those at-home things. We're going to see how that works out. And then after that, we only have 1 week. That's it. It's like we're almost there. So I don't know what we're going to do on that Monday yet. And then we have the final exam. I mean, I know what I want to do, but I'm not going to put it on the board yet because I'm not sure how this is going to go. So, all right, that's just a layout of what's going on. Just remember that the review for exam 2 is posted in Canvas. The review that I put up does not have polynomials on it, so I will have to add some stuff with polynomials. I'll add another document for you to look at. That'll give you an idea of what to get ready for. Okay, let's get started. So we have today, we're covering quadratic functions and applications. So I thought again I'd try and start off class with something that piques your curiosity a little bit. Does anyone have a textbook? Anyone have like a big, thick textbook with them by chance? Nobody carries textbooks anymore. Let me see if I can't find one real quick.
Would this work?
That might. Let me, but I'm going to abuse it a little bit. So let me grab something else. Hey, can I just borrow a book real quick? Okay. Okay, I will bring this back. Okay, here we go. So Yeah, this is a book, we used this like 10 years ago, so I can destroy this if I want. All right, so I have this textbook and I have this piece of paper and I'm going to drop them, right? And you're going to try and predict which is going to hit the ground first. It's going to be pretty easy, you think? Okay, so the book, let's see. All right, so the book hits the ground first. Now, why? It's heavier?
Air resistance.
What's that?
The air resistance.
Air resistance. So does it have anything to do with the weights? Okay, so it turns out that on Earth or on any planet with gravity, all objects will fall at the exact same rate, regardless of what they weigh. All right, now that's hard to believe here because you saw this drop a lot faster than this one. But it does not have to do with weight. It has to do with the air. The air is actually what's making this one drop slower. If the air was not here, if we didn't have air in the room, these two would drop exactly at the same, and they would hit at the same time. When we went to the moon, we put a couple of human beings on the moon. One of the first things they did was went out there and did a video of the astronaut holding a hammer and a feather, and they dropped them and they both fell together because the moon doesn't have an atmosphere. There's no air on the moon. So that was just to kind of like prove the point, you know, like we already knew it, but it was just kind of like to prove it. So to convince you of this, that it's the air and it has nothing to do with the weight, if I put this piece of paper on top of the book and drop them together, then if you think that it's because the book weighs more, then what should happen is that the book should start to fall away from the paper because it's going to drop faster, right? Let's just see if that happens. So they fell together, right? And there's no, I didn't go put a piece of tape on this or anything, like it's just, you know, it's right there. So they fell together, right? And that's because the book was moving the air out of the way, and so the air had no impact on this anymore, and so they could fall together. So if you take air out of a room, or if you neglect air, okay, if you just act like it's not here, which it is here, right? Thank goodness. But if the air wasn't here, everything would fall together. And that means that we should be able to come up with some sort of equation that would tell you how far something has dropped after a given amount of time, because it doesn't matter if it's a piece of paper, a feather, a hammer, a rock, everything should drop the same if you're neglecting air, right? So we actually do have an equation that does that. It's this right here. Let's do it this way. D of t equals -16 t squared plus, just look at it for right now and I'll explain everything in just a second, okay? But that's the equation, all right? And we will actually go into this when we do the applications of quadratics. I'm going to put this back on the board and we're going to explain what everything is. But I want you to notice here that the only variable in the problem, the only variable is the t, all right? So this is t, this right here is a variable, this is a variable. This right here, v naught and d naught, that's what that little zero means, is your initial velocity and your initial distance or height. If you want, you can look at d as being height. So what that's saying is, give me how high off the ground you're going to start, okay? So like, let's say we start by dropping something from 6 feet, all right? Then this would be a 6. And then this number has to do with whether or not you apply any sort of force to the object before you drop it. For example, if I drop these two pins together, they should go the same, right? But if I kind of throw this one down, right, and just drop this one, then of course that one gets there first. I gave it an initial velocity, and that's what this number is. So if I give this pin a little bit of a push down, this is going to be a negative number that we would put here. And I would have to know what it is, how much I push by. Or if I, instead of pushing it down, I kind of throw it up, then it's going to go up and then come back down, right? So then this would be a positive number. But those two things are always given to you. You're always going to have those. And then once you have these two numbers, can you see that this is a quadratic, right? And so on any planet, any planet, if you take out air, if there's no atmosphere, then you are going to have a quadratic equation that tells you like how high something is after a given amount of time. This -16 is the number that we use on Earth. If you're on the moon, this number changes. If you're on a different planet, this number changes. So this number is impacted by gravity. Understand? These two are just have to do with the actual problem, the way it's presented to you. But it's a quadratic. So if it's a quadratic, then we should probably take some time to study what quadratic functions look like. And that's what we're going to start with. We're going to start with what do quadratic functions look like when we graph them. You know, they're not straight lines. We're going to talk about their characteristics. We're going to take our time finding all the important points on a quadratic function. And then after that, we'll do an application, all right? And we'll actually be able to predict how long it would take for something to hit the ground, things like that. Now, this is without air, right? This is no air. So what happens if you want to have air? Well, then this formula gets more complicated, all right? And it's no longer exactly a quadratic. And that's why when you look at a physics book, all the formulas look very complicated, right? Because they start out with very basic ideas, no air. Then they say, okay, let's put the air in there, right? Okay, let's let the object start spinning. You know, you start throwing in more complication into the problem, the formulas become more complicated. Make sense? Okay. All right, so we are going to act like there's no air. And for certain objects, really air has very little impact. Like if you drop, you know, a rock in a bowling ball, the air will have a difference on the two, but it's negligible. Now a feather in a bowling ball, that you do have to factor in the air, if that makes sense. All right, so let's talk about quadratic functions, their important characteristics. And I know a lot of you have already seen quadratic functions, but all quadratic functions that we deal with are going to look like this. And that should look pretty familiar to us because last class we talked about how if we ever have a quadratic equation, right? This is a quadratic equation set equal to 0, that we can always find the solutions to this, right? We could use factoring or we could use a quadratic formula for that. Yeah? Am I recording? Yes, okay. So this right here is, remember this side right here is really like the y. So this is like y equals this, right? And therefore, if we were to graph this, we would have the x-axis, we would have the y-axis, and these look like what? So I know a lot of you already know what these look like. They're called parabolas. So what does a parabola look like? Like a U, almost like a U? Okay, so quadratic functions are going to look like this. That's the general characteristic of a quadratic function. Or it is also possible to have a quadratic function that looks like this. We are only going to deal with these two. There is such a thing as a quadratic function that looks like a U sideways, like either this way or this way, but we are not going to deal with those in this class. Only parabolas. Ooh, I always forget to silence my phone. I apologize. We're only going to deal with quadratic functions that open up or down. Okay, so this opens up. Does that make sense? This one opens down. Smile, frown, however you want to look at it. Now, does anyone know how we will know whether or not it's this one or this one? There's one thing that we have to look at. What positive or negative? It's one of these. It's either A, B, or C. So which one is it? It's the A. Okay. If the number in front of x squared, okay, not the x squared, if the number in front of it when it's given to us, if that number is negative, it's going to open down. If it's positive, it's going to open up. So I'm going to put over here, this is the case if A is bigger than 0. And then this one over here is the case if A is less than 0. Does that make sense? Okay. Now, there are some other important points on the graph of a quadratic function. I didn't put up here what these are called, parabolas. Okay. Some important points that we are going to be interested in when it comes to a parabola are these points right here. okay, and over here it would be these two. These would be like the x-intercepts of our line, right? If we had a line, we could find the x-intercepts. Same thing here. These are called x-intercepts. And how do you find the x-intercepts? How do you find the x-intercepts of a quadratic function? Well, how did we find the x-intercepts of a line? When we had a line like ax plus by equals c, I showed you a technique. To find the x-intercepts, you do what? Set y to 0, right? You set y to 0? Well, you do the same exact thing here. If you have a quadratic function and you want to know where it hits the x-axis, you're going to set y equal to 0. Well, y is this side, right? So if you do that, you're going to wind up with this equation. And then you'll do the quadratic formula or whatever it takes to get the x-intercepts. That make sense? So to find these x-intercepts, you're going to set y equal to 0, right? Which will basically give you the equation ax squared plus bx plus c equals 0. And we've practiced this, so this step should be something we've seen now, right? Okay. So those points are important. Now, there's another point, and that would be this point right here. What is that point called? It's this one right here. That one's called the Y-intercept, right? Both of these parabolas have Y-intercepts, right? So how do we find Y-intercepts? Same process with the line. We set x to 0, right? You set x equal to 0. Now, check this out. If I set x equal to 0, what am I going to get? If I were to look at this and let that x be 0 and that x be 0, then what's left? C, right? So this c right here should be my y-intercept. It turns out it is. As long as this is written this way, then the c will always be your y-intercept. So there's not a whole lot of work that you have to do to get the y-intercepts. For the x-intercepts, yes, you do have to work for them, all right? But the y-intercept is almost given to you. All right, what else? There's one other important point on a parabola that is different than anything that we had with lines. There's one thing on there that a line doesn't have. Like lines have x-intercepts and y-intercepts most of the time. But what is it about a parabola? What is something on the parabola that would not be on a line? The curve, what do you mean? The vertex. Okay, so it's called the vertex, but what is it? Can you explain?
Highest point or lowest point.
Okay, so here it would be the highest point, right? The actual highest point on this little hill, okay? That point right there, we call that the vertex. See, lines don't have vertexes, right? This would be the highest point. This would be the maximum point. So if you think about my pen again, and remember I said if I just let it go, it's going to fall, right? And the highest point would be where I dropped it from, yes? But if I throw this up and then it comes back down, it's got to go up, it's going to hit a highest point and then come back down, right? Somehow this quadratic, this highest point is going to give us that, right? The highest height that it gets to. And then over here, it actually looks pretty close to the y-intercept the way I drew it, but I would say it's probably a little bit lower over there, right? That would be your vertex. I know it's starting to turn to a spaghetti factory up here. Vertex, okay? And the vertex, unfortunately, there is not an easy way for us to get the vertex. Like, you know, we find the x-intercepts, we set y to 0. To find the y-intercept, we set x to 0. To find the vertex, there's not a simple method to do it unless you do some calculus. But the good news is that the people have already done the calculus and they were able to come up with a formula for us. So we're just going to use the formula. It's a gift from calculus, all right? So the vertex, I will give you the formula for it, but just keep in mind that you will need a formula for this, all right? And it will be called the vertex formula. And I'll provide that to you in a second, all right? Okay, so before we start going and trying to graph some of these, let me ask you something. If you have a parabola, whether or not it's up or down, do you have to have a vertex? If it's a parabola, is it a necessity to have a vertex? If I tell you you have a U that opens up or opens down, do you have to have a vertex? Yes, okay? All parabolas, all quadratic functions will have a vertex, a single vertex, all right? It'll either be the highest point. Oh, I didn't put this over here. This one would be the minimum, wouldn't it? That would be the minimum point. That would be the lowest point. Okay, so all quadratic functions must have a vertex. How about y-intercepts? Do all parabolas have a y-intercept? Is it possible for me to draw a U like this or flip it over like this and not hit the y-axis? It seems like maybe it would be, but see, there's something subtle in this picture. When I draw this, let me see. You know the letter U? The letter U? It's almost like these two sides fall between two lines, right? Well, with parabolas, that's not what's happening. This U continues to widen. There is no restriction. It has to widen. These arrows mean that it keeps getting bigger and wider and wider and wider. And same with this right here. So it's not exactly like a U where it turns up and then you're kind of stuck between two things. It keeps spreading out. Okay? I'm telling you that that's a property of parabola. So let me ask you again. Is it possible to draw one of these without ever crossing the y-axis? No. It would be impossible. All right? So like, let's say you had this over here and you try and draw your parabola like way over here. Okay? Let's say you say, okay, it's over here. Well, this is going to keep widening out, widening out, widening out, widening out. I'm going to hit the y-axis somewhere way down there. I'm going to hit it, okay? So it is impossible to have a parabola without a y-intercept. Can you take that on faith? Yes? Okay. How about an x-intercept? Do you have to have x-intercepts? No, you do not. Okay, so that is the main thing that I want you to get from this right now. Not for everything, but when I'm asking you to, does it have a vertex? Yes, has to. Does it have a y-intercept? Yes. But when it comes to x-intercepts, you are not guaranteed x-intercepts. Okay, so let's talk a little bit more about x-intercepts. There are 3 different scenarios that you could have when it comes to x-intercepts. You could have 2 of them. Okay, that would be like the picture I drew right here, right? I have 2 x-intercepts. The other one I drew that I erased, open down, had 2 x-intercepts. So a small picture of that would be, this scenario right here. Hits twice. Okay, what's another possibility? Could I have 3? I mean, if you draw a U, you can hit it twice, but there's no way you can hit it a third time unless you kind of curve back around. Then it wouldn't look like a parabola anymore, right? Those are polynomials. That's what we study after this. So 2 is possible. What else? None? Is that what I heard? None? Okay, so none would be, let's say I put my vertex here. That's the lowest point, and make it open up like that. That would be an example of a parabola that would not have any x-intercepts. I could also have done it, like put my vertex here and have the parabola open down. In both of these cases, do you agree we have no x-intercepts? Okay, and then what do you think? Do you think it's possible to have 1? And how would that happen? Yeah, what if your vertex is actually on the x-axis? Then you have that scenario, right, where it just touches, the vertex just touches. And then you'd have 1 x-intercept. So how do you think we would actually know which of these 3 cases it is? Think about, what do you need to do to find the x-intercepts? What do you have to do? Set that thing equal to 0, right? And that means you'd use a quadratic formula, right? And didn't we have some situations come up with quadratic formulas, with the quadratic formula? Let me put that quadratic formula back up here for you so we can take a look at it. Here was the quadratic formula. So when we're trying to find the x-intercepts, we try and solve this, right? And to do this, we use this formula right here. All right. So let's talk about this piece right here. Just this. I want you to focus all of your attention on this right here. This actually has a name. It's called the discriminant. Discriminant. I think I spelled that right. Discriminant. What? You're probably right. Yeah. It's a math class, not an English class. Let's see if your thing talks about it. Discriminant. Yeah, that's right. Okay. I've done my English for the day, for the week. All right, so this is actually called the discriminant, and it actually tells us which of these cases you have. So let's just think about this. What if the discriminant, I'm just going to put here DISC, how about that? Discriminant, what if it is a positive number? Okay, so let's say this is a positive number. Can you take the square root of a positive number? Yes, and you're going to get an answer, aren't you? Then you'll have something plus or minus something, right? Which means you're going to have two different scenarios. Remember how we had like the plus case and the minus case? We get two different answers. If that discriminant is positive, we're going to get two answers, and that means we're going to have two x-intercepts. All right? So that would be two x-intercepts if that happened. What if the discriminant is 0? The number 0. Now, didn't we have that on someone, I think, on one of the problems over there, didn't they have a discriminant of 0? Or I could have sworn we did come across this once. If the discriminant is 0, what happens? This is just 0, right? So you're doing plus or minus nothing, which means you don't even have to look at it. So all you get is negative b over 2a. And that's one answer. So this would correspond to one x-intercept. And then finally, if the discriminant is negative, a negative number, then we said it would have no real solution, right? Imaginary numbers. And that would correspond to this, wouldn't it? No x-intercepts. And this is what gave imaginary numbers such a bad rap for so long, is that it was like the people who believed that like the square root of -1, they were like, oh, let's call that I. And the people who didn't like that were the people who were like, look, you're trying to find the x-intercepts of something that doesn't have x-intercepts, right? The formula spits out a negative number. We should have no x-intercepts. Like I doesn't make any sense. And the picture matches it. So, but eventually they worked it all out. And like I said, this is a very important thing in mathematics. All right, we good? We understand kind of what's going on? All right, let's just dive right in. What we're going to do is I'm going to put up a quadratic function. I'm going to ask us to graph it. And what I mean by that is I want a very detailed picture of the parabola. I want the x-intercepts, the y-intercept, the vertex, and yeah, that's it. Just a good picture, all right? So here's the first example. And I think I have one ready to go here. Can y'all see that okay? Let me dim one of these lights. There's always something here. All right, so we're going to take this function and we're going to graph it, all right? So I like to follow steps, all right? I like to give everyone a set of steps to follow. I recommend that on the test you do these same steps. In fact, I think on the review it says use the 7 steps, that we did in class to do this problem. What I don't want is just a little picture without any work, all right? Because I know some people have graphing calculators and you just graph this and it's over. That's not what I'm looking for. I'm looking for, can you follow a procedure? All right, so the first step, what we're going to do is we're going to determine whether or not it opens up or down. All right? That's the first thing we're going to do. Does it open up or down? That's also, you could also look at that question as saying, does this parabola have a maximum or a minimum? Right? Because if it opens up, it's going to have a what? Minimum. And if it opens down, it's going to have a maximum. All right, so how do we determine for this one? Well, you can see what a is, right? The number in front of x squared is -2. So since a is -2, and that's less than 0, it opens down, right? All right, that's the first step. Second step is to find the vertex. And what do you need in order to find the vertex? A formula. And I haven't given you that formula, all right? So just on the side here, let me just point something out to you. The vertex is for us is going to be this point, right? It's going to be the highest point on our graph. That point has like an x and a y coordinate, doesn't it? Like how far you move left and right and how far up and down. Because it's such an important point, we actually we don't call it xy, we call it hk, all right? We give it special letters. H and k they represent the x and y coordinate of the vertex, all right? So here's the formula. If you want to know what h is, all you have to do is calculate -b divided by 2a. Now again, don't ask me why, because this is a gift from calculus and they have to come up with that formula in calculus, and it's not that hard to do in calculus, but that's where it comes from, all right? All right, so this right here is what we need to calculate to get just the h, okay? That'll give us just h. Now how do we get k? To get k, we have to do another calculation. We have to take the answer we just got, okay? We have to take this answer and we have to plug that answer back into the function for x. So let's actually do this, all right? What will this be right here for us with this problem? What's -b divided by 2a? Well, what's b for us? We never labeled it up here. Let's go ahead and label it. A was -2, right? B was what? 4, and C was 1. Okay, so what we're supposed to do is take -b, which is -4, and divide it by 2 times what? 2 times -2. That's -4 over -4, and that's +1. Right? +1? We good? Now, what do we do with that answer to get k? Plug it in. So we want to take 1 and plug it into the function. So I told you I would give you a formula for vertex, right? Here's the formula, right? That's your h, that's your k. But this is us actually using that formula for this problem. So let's plug 1 in here. Just be careful here. We've got -2 times 1 squared plus 4 times 1 plus 1. And what do we get there? 3. You should get 3. So what is our vertex? The point 1, 3. So I'm going to put it right here. It's the point 1, 3. That means if I could ask you to graph this point, it means you go to the right 1, you go up 3, and you put a dot there, right? Okay, that's going to be the highest point on our graph, right? It's the maximum because this thing opens down. All right, next step. Now, as long as I've been teaching, which is a long time, this third step is something that I've only seen me do this. I've never seen a book do this. I've never talked to a tutor or something that does this. So I'm telling you this because if you go to get help, they're probably going to be like, what are you doing at this step, all right? But let me try and explain the rationale of this next step. Right now I know I have a point on my graph, right? I know that that is the highest point on the graph, and then my graph opens down. If I were to just draw it real quick, a sketch of this, wouldn't I be able to tell how many x-intercepts I should have? Let's just see. Let's just do it. If I just do a quick, so this is going to be a quick sketch. Quick sketch. This is not your final answer. All right? Quick sketch. That's K. Quick sketch. All right? So I just real quick draw an XY axis. I go to the right one. I go up 1, 2, 3, and I put a dot. There we go. Now my parabola is supposed to open down, right? From this point, it's supposed to go down. Now, I don't know exactly where it hits, but I can tell you right now that it has to have 2 x-intercepts, right? What if it had opened up at this point? You would have none, right? And that means you shouldn't go trying to find them. Does that make sense? This just saves you a little bit of time, because if you don't do this step and you don't have x-intercepts, you're going to spend 5 minutes, 10 minutes setting this thing equal to 0 just to get a negative underneath that root. Like, that's what would have happened. But here we know that when we do the quadratic formula on this, we are going to get a positive underneath that root. That discriminant should turn out to be positive because we have to have 2 x-intercepts, right? So that's my third step. Quick sketch. This determines number of x-intercepts. So from this picture, we have 2, right? 2 x-intercepts. So what do you think our fourth step is going to be then? To go find them, right? So our fourth step is to find x-intercepts if you have them, which we do. If we didn't, we'd skip step 4. All right, so let's do it. We do have 2 x-intercepts, so I'm going to take my function. I'm going to replace y with 0, which means I'm just going to set that whole thing equal to 0. So here's my step 4. Negative 2x squared plus 4x plus 1 equals 0. Now, I could try factoring first, right? Can't I always do that first? Try factoring. But I do not believe that's going to work. You're not going to be able to come up with 2 numbers that multiply to be what? They'd have to multiply to be negative 2 and add up to be 4, and you're not going to be able to come up with those numbers. But they exist. There's 2 of them. There's 2 numbers that do that. We just can't think of them. So we use the quadratic formula. X will be equal to negative b plus or minus the square root of b squared minus 4 times a times c, the entire thing divided by 2 times a. Now, we've done that before, right? That was your homework assignment. We did a few of those in class at the end last time, right? How did y'all feel about that? Did you feel like you were getting a hang of it after a while? I mean, I know it's kind of like once you get it, it's like you can just kind of say, okay, I know how to do it. You just have to be careful with your signs, right? Take your time. So this is going to turn out to be 16 and then what? Plus 8. Okay, this is going to be a negative 8, but then you're subtracting it. So we're going to have negative 4 plus or minus square root 16 plus 8 all over negative 4. This is negative 4 plus or minus square root of 24. That's 16 plus 8 all over negative 4. And then this is where we get the calculator out. So everyone should be okay on their calculator getting square root of 24. I'm getting 4.8989799486. So let's just say for this class, we'll round 1 decimal, all right? So I'm going to put 4.9. So we have negative 4 plus or minus 4.9 all over negative 4. And now we have 2 different scenarios to look at. We have the plus and we have the minus. Can you see already that graphing quadratic functions is a process? It is a procedure, right? And I think I alluded to this in the beginning of this class. You know, nobody in here is a math major. Nobody in here is an engineering major, right? Everybody is pretty much in a different field. You'll never have to graph a quadratic function ever in your life, but it's about following procedure. Can you learn a technique, a process, and then follow it? It shows you're teachable, I guess. All right, so here we go. I'm going to go -4. I'm going to go plus 4.9. Then I'm going to divide that by -4. Then on this one, I'm going to go -4 minus 4.9 and divide that by -4. So let's see what I get here. 0.9 divided by 4. Yeah, that's fine. 2, 3. If you want to go 2 decimal places, that's fine. 1 decimal place. You could say 0.2 here. I'd be happy. 2.23? Okay. There we go. Now, I know that when we were doing these radicals the other day, some of you were saying, okay, well, you could break that up, and that could be like 4 times 6, and then that would be something like 2 root 6. And I said, yes, this would be the exact answer, and that's great. But the problem is, like, if I'm trying to find the X-intercept, like nobody's going to be able to look at that and tell me that that's these two numbers. And you're going to easily be able to put them on an x-axis. That's why we just go to decimals, because it's just easier to graph. All right. Okay, so we have now found, whether or not opened up or down, we found the vertex, we determined we had 2 x-intercepts, and we found them, right? What do you think's next? This would be step 5. No, these should be where we hit the x-axis. These should be points. These should be on my x-axis. I should have -0.23 comma 0. That should be a point because the y was 0. That's how we got here. And then this one should be 2.23 comma 0. Go back to the picture that I had up earlier. We had vertex. We said we always had to have a vertex, right? X-intercepts, we may or may not have them, but we've found them. What else was part of the graph that we were guaranteed to have? A y-intercept, right? We haven't done that yet. So let's find the y-intercept of this graph. Are there any questions before I move on? Okay, where are we at? 5. The y-intercept. And I told you that finding the y-intercept, you'll always have one, right? You'll always have one. And if it's written this way, the y-intercept is just c, isn't it? Okay, so it's just, what you'll write here is 0, 1. Because your x is 0, that means your y is 1. So that will always be 0 for the y-intercept, and then whatever this c is, this is c, right? Now, sometimes we talk about something else on a graph of a parabola. Don't write this down, but sometimes we talk about this imaginary line that cuts right through the center of a parabola. And we have a name for it. It's called the Axis of Symmetry. And all it means is that when you draw a parabola, if you draw this line, dotted line through the vertex, that if you reflect this over, it should just land right on top of itself. So it's like a mirror image. The parabola is a mirror image of itself over this line. And sometimes in my class on step 6, we go find that. We find the axis of symmetry, but we're just not going to do that. We're just going to go straight to step 6 being, let's sketch it, all right? Let's just draw the sketch. So we're going to have a 6-step process instead of a 7-step process in here. When you look at your review for this test, it's going to say use the 7-step process. That's 6 now, okay? So here we go. Let's sketch it. And what we want to do is we want to have a pretty decent sketch that labels everything that we've found. And we have to think a little bit about what our x and y axis needs to be. So let's think about the vertex. Where was the vertex? It was like 1, 3, wasn't it? 1, 3. So I need to be able to go to the right 1 and up 3. Agreed? And then my y-intercept is at 0, 1, which if I go to the right 1 and up 3, there's where my vertex would be. My y-intercept would be about here, wouldn't it? Now, where are my x-intercepts? 2.2 this way, and then negative 0.2 this way, right? Now, here's why I'm saying this. You don't want to draw a graph that looks like this. 1, 2, 3, right? 4, because you know that the highest you're going to be is 3, right? So you probably want to make your 3 be somewhere up here. Also over here, you don't want to be doing like 1, 2, 3, because you're going to need to go to the right 2.2. And so if you do it like this, it's going to be a tiny little parabola in here, isn't it? So you want to kind of think it through a little bit. You have all the information. You want your picture to be easy to look at. So what I'm going to do is I'm going to say this is 1, this is 2, this is 3. Won't that cover my x-intercept this way? And then if I go this way, negative 1 be about right there. Close enough. And that should cover my x-intercept the other way. And then I need to go up 3. So 1, 2, 3, 4. And by the way, this length right here, if I say that's 1, this would be 2, this would be 3. This length does not have to be the same in the y direction. In other words, I could make this 10, 20, 30, and that would be okay. So if this is 10, if this length is 10 in the y direction, that's fine as long as you're consistent the whole time. This can be 1 in the x direction as long as it's consistent the whole time. Okay, so they can be different from one another. This is what we call scaling the axes. But I don't need it in this case. I can just do that. Okay? Now, start off with the vertex. So my vertex right here, I'm going to label it 1, 3. I'm going to even say it's my vertex. And then, what should come next? It really doesn't matter, but you know, do the x-intercepts. That's what we found next, right? So the x-intercepts were at 2.23. So here's 1, here's 2. Halfway would be 2.5, wouldn't it? Half of that would be 2.25. So we're just ballparking this, okay? We're just getting close, that's all. And I will label this. I will label it 0, 2.23. Why do I label it? So when my instructor is grading it, they can see that I have clearly found the correct x-intercept, right? And then over here, negative 0.23? Would be, if that's halfway, that's a quarter, so I don't know, about right there. And that would be 0, negative 0.23. Was it 0.23? It was, right? Okay. And I had one more point. The y-intercept, which is at 0, 1, which is this one right here, right? All right. So now we get to draw it, all right? We get to draw this parabola. Now, we skipped the step on the axis of symmetry. I'm not going to ask you to identify it, but I do want you to think about it when you're drawing your picture. Your parabola, there's your vertex, right? Your parabola must go and look like a U that goes down like this. It must go through this point, and then continue down forever, right? So I'm going to kind of start by doing this side, because I have 2 points over here, don't I? To go through. And I draw a little arrow like that. Now what you want to do is you want to try your best to do a mirror image of that on the other side. It doesn't have to be perfect. What you don't want is something like this, okay? Like that doesn't look, you know, too great, right? Or you don't want something like this, right? You want this to look like a mirror image of itself across the other side. So you do your best, all right? All right, so I would, something like that. We could argue whether or not that's good enough, but I think that's fine. All right? Now, something I will take off for if I see this. If you do this. And that's, you can't have, parabolas do not have sharp corners, all right? Parabolas are like roller coasters, right? They're nice and smooth and curved. They do not have a jagged corner to it, all right? That would actually be a different type of function. Most of the time when you have that happening, it's an absolute value function, and this is not an absolute value function. So if you draw a V instead of a U, there will be some points deducted.
X-intercepts backwards.
I don't think they're backwards.
0, isn't it 2.230?
X-intercept.
Oh, I knew what you mean now. I wrote these backwards. Yes, that I did right backwards. Thank you for catching that. This is, I never labeled my Y-intercept, 0, 1. Yes, please change these. These are written wrong. Okay, there. Okay, so if you did that right there, if that's what you had on the test, with all your work preceding this, that would be full credit right there, all right? Some things to pay attention to. Let's say you're doing a problem and you get a vertex right here, okay? And then you go and you put your X-intercepts, and they're right here, like that. And then you get your Y-intercept, and it's right here. You should be thinking what at this point? Something's wrong, right? Because your parabola can't do this, okay? It can't do that. So this means something's wrong, right? Don't try and draw something that doesn't look like a U, because those are where your points are. You need to go back and look at your, how you got your points. Another one I see a lot is something like this. You get a vertex here, and then you'll get X-intercepts like this. And then, students will draw some sort of parabola that looks like that. They have to be symmetric. They have to be mirror images. And if it doesn't look like it's going to turn out that way, most likely this mistake right here is that your signs were wrong in the quadratic formula. Something was wrong with one of the signs and they're backwards. Something like that. So those are like red flags to look for when you're trying to graph these. All right, what time we got?
Is this going to have like pre-made graphs like the last test?
The review has some pre-made graphs. I haven't made this test, but most likely I will do a pre-made graph. And I think on the last one, there was one problem where the line went off the graph, so you had to have changed your scale a little bit. I'll probably make this one where everything will land on your graph nice and clean. All right, I think we should do another one. They take a little while, right? Let's do this one. This one looks interesting. All right, so it's 11:55. Let's see how long it takes us to get through this one. All right, first step. What does this one do? What are we looking at for the first step? It goes down again, okay? So A is -3, therefore it goes down, all right? Second step, vertex, right? That's our second step. H is -b over 2a, and k is equal to f of h. So there's our formula for vertex. If we're keeping score here, A is -3, B is -30, and C is -82. So here, when we go to this formula for H, we're going to do -b, which is what for us? +30. Right? It's the opposite of whatever b is. And then over 2 times -3. So what does that turn out to be? 30 divided by -6? -5? We good? 30 divided by -6? And now we have to plug that into the function. We actually have to plug -5 into this. See, this is where all the little order of operations and all those little things, you have to get it right. You all right? You're squinting your eyes. You okay?
Oh, yeah.
Okay. All right. Can't help you there. Sorry. All right, so now we plug in -5. So let's go in here. -3, -5 squared, minus 30 times -5, minus 82. I can't stress enough to you how you will never graph a quadratic function in your life probably after this, right? What I'm imagining right now is you're working your first job, your first internship, whatever it is in whatever field, and they're trying to teach you how to use the copier, right? The copy machine. And they take you to the copy machine, they're like, okay, if you're going to do this, you have to do this, 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 this. They give you like 8 steps to do something. If you're like, okay, and then you can't reproduce that, if they have to show you 5, 10 times, then there's something wrong with the way you process information. This is what this is about, processing information. I don't know if I'm picturing you at a copying machine right now. And then later on it becomes something else, right? Teaching you how to, who's got a major? Who knows their major already? What do you got? Medical what? So do you have an idea of what you, so what would that entail, career-wise? Do you have any idea yet?
Probably anesthesiologist.
Okay. Really? And you don't have to take math intensive? Really?
It's in our degree.
So anesthesiologists would definitely have to be able to process information pretty good. You can't accidentally over-sedate somebody. Oops. Right? Okay. Let's see here. This, what is that? We got to do this, right? What is that here? This is going to be -5 squared, right? Which is positive 25, but then times -3. So -75. And then here we've got 2 negatives here are going to multiply out to be positive, right? So plus 150. And then minus 82. And that's 75 minus 82 and -7? -7. So we have a vertex. Our vertex is -5, -7. That is a point on our graph. So what would be our third step? A quick sketch, right? So if I do a quick sketch and I go to the point -5, -7, that means I'm going to go to the left 5 and down 7. Notice I don't even care how far. I just kind of get it close enough. -5, -7. Which way does our graph open? Down. Ooh. Ooh. I wasn't anticipating this was going to happen. What does that mean? There's no x-intercepts, right? So when I go to step 4 for x-intercepts, I have none, right? And so you see I just saved myself quite a bit of time, right? I just saved myself quite a bit of time because I'm not going to set that thing equal to 0. I don't need to. I know I don't have any. So I'm going to skip that step. Y'all okay with that? Sure. What about step 5? Y-intercept. Now I guarantee have to have one of these, right? So the y-intercept for this would be -82, right? -82. And now I get to graph this. And I'm going to take my time to carefully contemplate how I'm going to set up my x and y axes here. So here's step 6. Here's my sketch. So look at that.